Okay, let me get started. The first question, I guess, is going to be, are there any questions? I guess the homework two came back. The homework two assignments were graded. The TAs posted, I guess, what the answers were and what the what the grading rubric was, and the important point was that every paper was graded by two different. Every problem was graded by two different TAs. And so we could compute a correlation between how what one TA gave and what another TA gave. And we found that there was certainly great agreement between the two of them. So I kind of believe that the homeworks were graded the way I wanted the homeworks graded. I'm hoping we're going to be able to post some representative, very good solutions. Okay, and so if some of you are, again, there's descriptions of what were common mistakes, they were lit or the weaknesses. There were, and we will post examples of a couple of good ones, so that if you wanted to look and see how you're doing, um, or let's say what would have been a better thing to do, maybe they will serve as models. Any questions? As I remember, the mean and median came out to around 70 on the assignment. Is that right? So, so that, so, you know, but deliberately, in order to get information from it, we don't want the assignment grades to be 100 because then nobody gets any information about anything. So, so we have had a standard where we were, how we were doing it. Any questions about homework two? Okay. Good. Okay, let's now look forward a little bit. First of all, any questions about homework three? Homework three is now out. Any questions? Any people get started on it? Any questions or comments about that? Anyone in TV land? Okay, so this should start to rear on your consciousness. I guess this weekend, next class, next period, Tuesday, is, I guess, fall break. Am I correct? So, what would be a good relaxing thing to do over your fall break? I think it would be the homework three and the working on your project proposal. Any questions about projects? A question? Okay, there's a question here. Let me see. I have a question about the end term timings. Okay, ask me this question.
Professor, as I recall correctly, the timing currently is at 8 o'clock in the morning.
Yes.
I was wondering, can it be shifted to a somewhat a little later time, like afternoon? Because 14th December, as I know, it will be very much cold and winterish. And to come from Port Jeff to campus, that would mean that, like, if the exam end up in person, then we will have to take the train at 6 o'clock, 6:30 to come.
Okay, the exam, first of all, it will be cold for everybody. I walk to work usually, so you're not going to scare me off about the cold. But the main thing is that with a class this big, there's no way you can change the timing of it. So that's one I want to make clear. The exam is going to start at the time the university tells us we're going to start the exam, and it's going to end 2.5 hours later. So if it's necessary to prep by what you call it, getting warmer clothing or arranging to crash at a friend's house that's local so you don't have to take the train or use Uber or something that morning. That's the timing, unfortunately, I have no control over. Okay. What I did have control over was whether I wanted to try to have a live exam in a room or a remote, and it was clear from the vote that a non-trivial majority of you preferred the exam to be online. So we're going to make the exam online for everybody. Okay, for consistency. In fact, that actually may answer your question. You don't, in some sense, have to, come to think of it, worry about getting here in the cold, because if you have Wi-Fi where you are that is reliable, you will be able to take the exam there. Okay?
Yeah, noted. Thank you.
exam will be online. It will be exactly when the university scheduled it, and there's no freedom to change times. Any questions? Any questions about projects or anything like that? Okay, if that's the case, then I'd like to go and finish talking about our notion of statistical significance testing. Last time we showed a bunch of formal statistical significance tests, things like t-test and the KS test, um, and then held out hope of a kind of a more general computational approach to getting an idea whether how strongly you believe, okay, that some kind of an observation is real, okay, and it was the permutation test. To recognize that, what did we do? You had a target variable. Here it was, let's say you wanted to know whether men really have taller heights than women after some observations. Here you would observe men. Here you would observe women. Okay, you measured heights. What was the idea? The idea was we're going to compute a statistic that reflects the observation that women are that in your data the men were taller than the women. And how did that work? Maybe we took the average height of people labeled men minus the average height of people labeled women. And then what we would do to see how much we believe that this was not a result due to chance, we would randomly scramble the genders, okay, which is the same in this case as randomly scrambling the heights, okay, and we would come up with a, different world where fake men and fake women had heights. We could compute what the difference between their average heights were, and that would give us the hope would be that if our observation was real, the random scramble should produce a less strong difference. If we do this for a large number of different random scrambles, or random permutations to be precise, what we're doing is we would get a distribution of scores. If the observed score is to the left of all of them, then we feel quite good that that isn't happening by chance. If we do a lot of random samples and we're to one side of the vast majority of them, this gives us some level as to what the probability is that something like this could have happened by chance. Okay? We don't need it to be the right of all of them to be interesting. But if you did 1,000,000 random samples and all but 50 or 100 of them, okay, were less extreme than what you observed, then your observation is probably not due to chance. Any questions about what the scheme of the random permutation test? The two components you need to do are you need to have a statistic, okay, that is measuring something about what your observation is. In this case, the difference of the average heights. Okay, if you were trying to say how good your model was, well, maybe it would be a performance score, an F score on some test set or something like that. And the other component you need is to, to have the ability to generate random permutations. And that's what I'm going to talk about in a minute. Any questions about what permutation tests are and how they work and what the idea here is? Okay. Now, notice that people are usually tempted to run permutation tests when they think they see something. And this gets us into a world which is kind of murky when we remember thinking about our Bonferroni correction. What was the idea of the Bonferroni correction? If you had a million hypotheses you were trying, and you saw one that stood out, it wasn't fair to say, look how amazing it is. This happens with a chance 1 out of a million. That was a meaningless thing if you tried a million tests. There are a couple of dangers in some sense with permutation tests. Statisticians are not crazy about these things. One reason is that you tend to apply them once you think you've seen something. And once you think you've seen something, that's sort of like a case of the Bonferroni correction, right? If you're looking at a bunch of plots and one suddenly shows up and looks great, well, how impressive is it? If you've looked at a million plots, maybe it's not so impressive. And that isn't something that would come out as a result of the number of permutations. The number of permutations don't know how many plots you've looked at. Okay? So I think that a permutation test is a good way to tell if you're seeing something. Okay? But in some sense, in a formal way, it gives you the probability that your data given what your assumption was, rather than in some sense what statisticians are interested in, which is the probability of the hypothesis given your data. And there's Bayes' law that kind of connects these things, but it's a little bit murky on some level. But if I need to test something complicated I see, is it real or not? How impressive is it? I do permutation tests. Any questions about permutation tests? Okay, one interesting question is, so what is a permutation test? You're going to have to do one. One thing you're going to need to do is to generate random permutations. And this is a fairly subtle problem. Okay? Subtle, what does subtle mean? Subtle to me means it's more complicated than it looks. It's easy to get wrong. Okay? I'm showing you two programs that generate a random permutation of n things. And one of them is right and one of them is wrong. Which one is right and which one is wrong? Take a look at this. Now maybe, I hope in TV land, I don't know if this is too blurry. If so, you can look at the original notes. But I can read it to you. Okay, first of all, how many people don't see even any difference between the two of them? Okay, what is the first one saying? It says, initialize an array from 1 to n. 1, 2, 3, 4, 5. Okay? Then for I goes from 1 to n minus 1, swap, the first one says, swap the ith value with a random element from either the ith position to the nth position. The other one initializes the entire array, again from 1 to n, does the same n minus 1 swaps, only instead of swapping the ith element with one from the ith, maybe it's better to move my eye over here. The first algorithm is going to swap the ith element after it's done it's on the third iteration. It will swap the third element with one of the elements from the third to the rest. The first one will swap the third element with any element in the array. Does everybody see it? The only difference between these two is whether it's a 1 or an I there. Which one of these generates random permutations and why? Okay. People see this one way or another? Again, when you're generating, what does it mean to generate random permutations? One thing is you want all the permutations to come out equally, right? That means there's n factorial different ways of, permutations. If you're generating permutations at random, they better come out equally, right? Does anybody have a vote here as to which one is right? Okay, what? You say the first one. Why is the first one right? They said the second one can generate the same permutation again and again. Okay. You're saying because it's considering a whole array, it generates it again and again. I don't know that I follow that argument. Okay. Your answer is right, but your proof isn't convincing to me. Okay. Okay. What does it say on the second? Some people on television say it's the second one. And on the second one, there's a debate. Does it make any difference? First, let me convince you it makes a difference. This is a graph I made where I tried both of those algorithms, generating 1,000,000 random permutations on 4 elements. How many permutations can be made on 4 elements? 24. Okay? So if you look at it, the blue algorithm, which turned out to be algorithm 1, just about all the permutations came out more frequently, equally frequently. On the, on the algorithm 2, it turned out that some permutations came out 7 or 8 times more often than other permutations. Okay? So it does make a difference. If you're really doing this for statistical reasons, they better be uniform. Okay? Any questions? Why is it uniform? Well, the first algorithm, what does it do? The first algorithm started with my array, and it picked a random element from from the first spot to the nth spot. Let's say that was 4. Let's say it came up with a number 4. We swapped in the array, and then we're never going to touch this spot again. Does everybody see that as I goes to 2, next time we're going to pick a random integer from 2 to n. The first element is clearly going to be uniformly picked from all the elements that are there. The second element is going to be uniformly picked from all the elements that are left. And that's true for every other element in the permutation. That's why this thing generates things that are uniform. Why does the second one generate things that are not uniform? To be honest, I don't really see it. Okay, completely, kind of. Occasionally I've seen it. Okay? One thing that's true with random processes is that it's a very subtle thing. When you're wrong, it's hard necessarily to argue that you're wrong. Okay? It's important to argue that you're right. That's why I gave you a proof this one is right. I couldn't give you a proof that this one is right, and the reason is because it's wrong. Any questions about it? Okay? So, what's the idea here? Now you should be able to conduct a permutation test because you know how to generate random permutations. You can generate a bunch of them, okay, and use them to scramble the labels on your data, okay, and then see what, find a statistic to show what is the thing you're concerned with. Plot that distribution, and your p-value, your confidence level, is going to be something like the number of things that beat me divided by the total number of experiments you ran plus 1. 1 for the real thing. Okay, any questions? Okay. So, what is okay, so any questions about permutation tests? I did want to spend more time on the idea of random generation, because random generation or random sampling is kind of at the heart of all statistics. Okay? And again, there are a lot of processes that are, people try to build things to do random sampling, and there's often biases in what they're trying to do. Here's a question. Okay. Any question in TV land? No. Okay. So suppose, let's say, you wanted to draw random samples from a circle. Okay? You want to do random samples of points from a circle. Let's say you want to measure the average temperature of the circle. You might imagine that you drew some random samples and you measure the temperature at these few points. And maybe the average of that kind of is supposed to capture the average of the circle. How do we go about taking a set of a circle and finding what you call it? Finding taking random samples from a circle. Does anybody have an idea how to take random points from a circle? You're saying using polar coordinates, okay? What is polar coordinates? I think I know what that means. I think what you're saying is you're going to start from the center. You're saying every circle is defined by its radius, right? And every point can be represented by an angle, every point can be thought of as defined by two quantities. One is the angle relative to the origin, and the other is the distance relative to the origin. And so what you're proposing is you will sample an angle. The angles go between 0 and 2 pi, or if you believe in radian world, 0 and 360. And the radius goes between 0 and 1. Is that correct? 0 and r, fine, for a circle of radius r. Does everybody agree that if we go through this process, sampling points uniformly in a range is an easy thing? You certainly have a random number generator that can do that, although how that works is kind of interesting. But does that polar coordinate idea generate points uniformly at random? I agree, if you pick an angle uniformly, and then once you pick an angle, you pick a point along that angle, you're going to get a point in a circle. There's no question about that, right? But does that pick the points uniformly at random? Which of these pictures looks like it's sampled uniformly at random? Let's start taking a look at this. I've got two pictures here of distributions. Okay, I sampled points. Which one of these looks like they're sampled uniformly at random? The one on the left or the one on the right? Does everybody agree the one on the left looks good? Was this generated by using a polar coordinate idea? I think everybody understands the polar coordinate idea. I claim the polar coordinate idea is what generated the point set on the right. Why is that? What's the problem with the polar coordinate idea? Okay, everybody took polar coordinates. People liked it, yeah? You're saying there's more points in the center, near the center. Why are there more points near the center? Because it's involved in every line? That I don't believe, actually. Every line has an angle. That's not something, so I'm not convinced by that argument. Okay? What?
For all various ranges, like from 0 to r, you consider different ranges, center is always involved. The pyramid consider.
Okay, you say that the center is involved. The center is involved doesn't sound to me like an argument. You could imagine a random processing scheme where you go to the center and say hello, and then do something different. The center is involved. But the act of saying that hello to the center doesn't necessarily an argument. Does anybody see what an argument is? Why that you get something like this? I'm going to claim the argument is this. Suppose I consider separating the points into things that are a distance of a less than half, okay, the radius, from the center versus the points that are more than a half of the way beyond the radius. By your polar approach, how many points should be in each bucket? You can imagine we can separate the circle into a world where there are, the radius is a half or less, which is a small circle, versus a donut. Okay? Okay? You're saying that when you use polar coordinates, what's going to happen? If you're sampling the radius uniformly, I'm going to claim by that process half the points are going to be within the interior. Half the points will be in the inner disk, and half the points would be in the donut. Do you agree? No. Why not? Okay. Right. So we agree that in terms of what we want, okay, you're saying that the inner donut, okay, is going to have the inner circle will represent 1/4 of the area, right? So we agree the area of the circle is 1/4. Okay, sorry about this. The area here is 1/4. That means the area of the donut is 3/4, right? That means that we should have 3/4 of the points in the donut and 1/4 of the points in the inner circle. Do you agree? What's going to happen when you sample the thing in polar coordinates? Half-half. Does everybody see that this is what's happening with polar coordinates? If you sample it, you're sampling it too frequently, the inner part too frequently. Okay? You're going to have, in principle, be able to pick every point. That was a good thing with the polar coordinate idea. But there is going to be a skew. Does everybody kind of see that? So this is a problem with random generation processes. They are subtle, okay, and you can get it wrong. Unless you do something that is provably right, okay? How can we, any questions about that? Okay? How can we sample this? Where did this one on the left come from? It came, again, this is what the problem was. It came from a different idea. It said, what if we take our circle and draw a box around it? Okay? Now, if I put a box in the circle, if the circle is within a box, and again, if I did this right, I should probably, again, I'm doing a bad job with my drawing, but I think I should have my box touch the boundaries here, right? Circle, okay. Circle, box that's touching it. Does everybody see this? This box is a 1-by-1 box where there are 4 points tangent to the box. Does everybody see that? What could I now do? How do you generate random points in the box? Pick an X number uniformly from 0 and 1 to 1 and a Y value 0 to 1 independently, right? I'm going to randomly shoot bullets at this thing. And then what am I going to do? I'm going to ignore any bullet that went outside the circle. Does everybody kind of see that? Now every point in the circle is equally likely to be there, right? That's what I did over here. I drew a circle, I drew a box around my circle, randomly sampled points in the box, and threw out all the ones that weren't there, that weren't in the box. right? That were more than a distance of 1 from the center. Or half, I guess a distance of half from the center. Any questions about that? Okay. Was this wasteful? How much waste did I have in doing it? Remember, if this would be it should be clear this is uniform. Okay. The question is it efficient? It would be a problem if a lot of the points, if I threw out almost all the bullets, right? What fraction of the points am I going to keep? It's something like the area of this thing. What is the area of this thing? Well, okay, if this is a circle of radius a half, what's the area of the circle? That I believe is pi r squared, which means I think it's pi over 4. Am I correct? So what does that mean? The area of that is pi over 4. The area of the whole box was 1. Pi over 4 is something more than 3/4, right? So that tells me that more than 75% of the points hit the spot that I care about, right? So am I going to do a little more work in random sampling? Yes, but not very much, okay? And I do end up with a uniform sample. Any questions? So this technique of doing a what you call it, Monte, basically to try to figure out get samples by putting in a box and doing a test, and basically drawing points from the box. This works well, provided the area of the item region you care about is relatively large relative to the size of the box. Any questions? Okay. So being able to generate random samples is a useful thing to do. Okay. Suppose, let's say let me show you a general technique to draw samples in 1 dimension from any probability distribution. This here is a normal variable, right? A normal distribution. What was a normal distribution defined by? It was defined by, remember, our mean and our standard deviation, right? Now, suppose I wanted to draw samples from a normal distribution. Okay, remember I did that actually when I used the KS test to test whether something was normal. If you wanted to know where the heights were going to be normal, were you going to do that, tell whether that? Well, you draw a sample, find what the mean of your observed distribution is. You find what the measured standard deviation is of that observed distribution. You draw random samples from that normal distribution. And then you could use the KS test to tell whether or not these samples are drawn from the same distribution as your observed heights. So that's one reason why you might want to draw samples from a normal distribution. How can we do that? Okay. Remember, I think I've convinced you that random generation is a subtle thing. How do you go about generating points from the normal distribution or any other distribution where you have a PDF for it? Okay. One thing that I would do, the way that I think is the right way to do it, is anything that has a probability density function has a cumulative density function. Does everybody agree with that? And the cumulative density function has the property that it goes from 0 to 1, okay, the density, and it starts from the smallest possible value to the highest possible value. How would I draw samples from the normal distribution? What if I draw uniform numbers from 0 to 1 and use them as a y, okay, on the cumulative distribution function? Then I'm going to ask myself, what is the X value that exactly realize that value, that Y, that value between 0 and 1? Does everybody kind of see what I'm doing? In my cumulative distribution function, notice that what made a normal interesting was most of the weight lie between 0 and 1, right? What does it mean when they say most of the weight lies between 0 and 1? It means that there's a wide range of probabilities such that if you were picking a probability, that probability would correspond to something between 0 and 1 in the cumulative density function. Okay? So what is the procedure here? The procedure to sample from any one-dimensional probability distribution is to convert it to a CDF, randomly sample Y values, which are uniformly distributed from 0 to 1, and then go find the inverse. Find out what is the X that generated this. Any questions? Do people believe that generates normal distributed variables? Yes. Is it between? No. So it's between the probability. What we're going to be sampling here is the probability. The probability, remember, what is it? What is a cumulative, what is a probability density function? Remember the PDF, the x-axis was, actually essentially z values, right? The y value was a probability of getting exactly that value. That was what the PDF was, right? The cumulative distribution, the interesting thing was that it ranged the probability on the y-axis always goes between 0 and 1. Because what is a CDF? It tells us for any value of x, what is the total probability of being less than x, right? And this has to go between 0 and 1. So what is our idea? Am I good? Are you guys good at taking numbers uniformly from 0 to 1? Yes, there's a random generator for that. So what are we going to do? We're going to sample the points according to probability uniformly. Once we pick the y value, which has to be between 0 and 1, that y value maps to an x value, okay? And that x value, okay, would, maps, that y value maps to an x value. And this is the sample you really want. This number between 0 and 1 was easy for you to generate. But you want the samples to be drawn from the distribution. You want the x's. Does everybody kind of get that idea? Now, how, for a given x, could you figure out what that y, for a given y, what that given x is? What? So the y value, again, you're sampling the y, okay? Once you've got a y, the thing that you want to return is the x that corresponds to that y. It's the inverse, okay? Now, how do you compute that inverse? Okay? Well, it depends upon how your distribution is given. If your distribution is given as a math thing, and you know how to compute the inverse of that, then that's something that you can do. That's the right way. What if the distribution is maybe something that you had observed? Maybe you had samples here, some weird CDF. How would you sample from this? If this thing is represented by a polyline, let's say, but what are you going to do? It's kind of like a binary search thing. If you have a Y value here, you want to know what's the X associated with it. You could, let's say, if you have the cumulative distribution here, what's the sum of the probability to here, to here, to here, to here, to here? You really want to now know if you have these cumulative totals, where does this number fit in that array of cumulative totals? That's kind of can be done by a binary search in general. Okay? Any questions about that? Okay? Conceptually, it should be clear that you want the inverse, and how you find the inverse depends upon how your distribution was given to you. Okay? Is it a real numbered thing, okay, where you have a where you have a formula for it, you can compute the inverse using whatever math you learned, okay? If the distribution is a discrete thing observed from data, then typically it is a process of you have an array of values corresponding to what the cumulative sums are at a certain point. You then do a binary search on that. Any questions? Okay, so you guys now are capable of, in some sense, randomly sampling from anything uniformly or anything that's kind of shaped nicely relative to a box. Okay, any questions? So, why do people sample things randomly? Well, again, typically one reason is simulations, and maybe I'm not going to talk about this because I'll talk about it very briefly, but just as an example, let's say I'm not going to talk about this, but okay, I'll talk about it, whatever. Again, you guys baseball playoffs are going on now. It's very exciting. We're all rooting, by the way, for my San Francisco Giants, who play on Friday against the evil Los Angeles Dodgers. So you guys know who to root for, and if you want to get into baseball, this is a good time to do it. But one of the kind of most famous records in baseball is something is kind of a hitting streak by one player. There was a great player named Joe DiMaggio. He married the actress Marilyn Monroe, if you know about such things. But he had a record that for 56 games in a row, he always got a hit. Okay? And this kind of is nobody else has ever come close to this. That's one reason why it's a very famous record. And the question of how unusual is it that if you are a hitter who's as good as Joe DiMaggio, that you should be able to go 56 games in a row without getting a hit, with always getting at least one hit. Now, you know how many times he got hits, you know how many games he played, you know how many times he got up in a typical game. You can average and say that a normal Joe DiMaggio would be expected to get a hit in almost 80% of his games. Yet somehow, for 156 game streak, he got a hit every one of these times. This should sound like a Poisson kind of process based on what we talked about. You want to know what's the probability that he was able to get a hit 56 games in a row when the probability of getting a hit was 0.8, and the probability of ending his streak by not getting a hit was 0.2. So you could work this out as a Poisson thing. But I got curious and I wrote a little Monte Carlo simulation. Monte Carlo is famous as the city that has gambling, okay? And random numbers and gambling are kind of associated with each other. That's why we call simulations based on random numbers to be Monte Carlo simulations. And what I did was I simulated 100,000 Joe DiMaggio careers. And a career was Joe DiMaggio playing as many games as he did, simulating that every game would have a 79% chance of getting a hit. Okay? And the question would be, in something that's a lot like one of your permutation tests, how many of these synthetic DiMaggio careers did he get a hit as well as he did? Again, this is the distribution of what should be the longest hitting streak in his career. This is where the record is that he achieved. Okay? And as you can see, it's really kind of an amazing thing that he was able to get a streak like that. According to our statistics, if you have over 2,000 Joe DiMaggios, you would need 2,000 Joe DiMaggios in order to get a streak that long. Just so we understand, the second best hitting streak of all time is here. That's why this is kind of an amazing thing. But bottom line is, by using random numbers in clever ways, you can simulate things, and for your purposes, you can evaluate the statistical significance of things. Any other questions? Any questions about random generation, permutation tests, anything? Okay. Good. So at this point, any questions? Okay, so at this point, I would like to change directions a little bit. And now I have a start to go into the next unit in the course. And that is, of course, a unit on data visualization. Okay, so one thing that is true about data visualization is that it's one of these things that is a lot harder than it looks. And I don't think people tend to see how hard it is until they see examples of good and bad visualizations. So in particular, on homework 2, everyone here had to do on their assignment a plot of something interesting in the data set. And I had the TAs show me which were the best and which were the worst visualizations. If you see your graph up here, don't be embarrassed. There's no names. And you're supposed to learn. Okay, so hopefully next time, once you recognize what's a good and bad visualization, you'll hopefully get some kind of an idea for it. Because I think this is one of these things that is surprisingly hard to do. People don't naturally make good visualizations. So let's look at some plots of the data from homework 2. Which was, remember, the security project, trying to figure out what operating machines got broken into or not. And let's see whether we have a good visualization or a bad one. Okay, here's the first one. I'm going to want everybody to vote on every figure. Is it a good one or a bad one? Okay. This one is showing us, the x-axis here is the number of cores on a machine. The y-axis is the memory on the machine. Okay, and I guess the red line is some kind of a trend line. Does everybody kind of see that? Is this good or bad? What do people think of it? Do they look at this and does this tell you a story? Do you learn something looking at this? I feel I learned something looking at this, right? What did I see? It looks like the core size, the memory grows somewhat superlinearly. I see a little bit of a curve here, okay? I'm interested in kind of outliers. The machines that have the really high amounts of memory all seem to have a lot of cores, okay? There's some kind of funny machine that has a huge number of cores and relatively few. But this is interesting. I can look at this and see something. Does everybody kind of agree, or any questions? Any ways that you could make this thing better, by the way? Does anybody see a way to make this any better? I think this is a good visualization. Does anybody see any limitations here or anything like that? One thing that, let's say, I'd like to probably see better would be to understand more of what's going on here, where most of the machines live. And you can't see that very well. Maybe by having, either zooming in on the interesting parts, or maybe by having this be a log type thing, I'd be able to see more of what's going on there. Maybe if I had color for the number of machines, I'd be able to, but, to know how many machines are really at every point. Because two machines with the same thing are going to get overwrite each other, right? But I think this is a pretty clear one. Any questions? Here was another figure that was related to system stuff. What do people think about this one? It seems to show on the x-axis the total volume capacity, which I'm guessing must be a disk thing or something like that. What's the y-axis? First, I don't know. And second, I think it's probably a frequency. Okay? I don't think I learned very much from this plot. Does anybody like this plot? To me, I don't think I learned that much from it, right? It doesn't tell me a story. I think it's just a one-dimensional presentation of data that's obscured by some desire to centralize something. Okay? So I don't know what this does. Any questions? Okay, good. Says, is this a histogram or a scatter plot? I am not sure. I am thinking, because these things look like lines, so thanks. I am guessing that this is some kind of I'm guessing it is some kind of a weird frequency count, where it's sort of centered, instead of having it be like a normal graph. My instinct is that instead of it being a normal graph like this, they center the values. But I could be wrong, okay? But it doesn't say anything to me either way. Anyway, if I can't tell that, that's a sign that there's a problem. Okay, here's another plot that a group did, which is telling me, I guess these are the versions of the app, which I guess means the, the version of the operating system. Is that right? Was by app, did they mean operating system, or what was app? What? Windows Defender. It wasn't the operating system, it was a product. I guess it was this was the version of the antivirus product. Is that right? Okay. And so what does this tell me? In blue, it's telling me how many machines had that thing, and the Y was what's the rate of detection. Okay, how many times people who had that version, what fraction of the times were they hacked? Okay, is this a good plot or a bad plot? People say good plot. Can you see something? Does this tell you a story? Okay, what stories do I see here? Seems to me everyone had this version. Why did everyone have that version? I don't know, but that's a phenomenon that probably needs some explanation, right? And it shows me something about how good each version is. Do we believe that these versions are worse, much worse than this version of App Defender? That's seemingly what it's trying to tell me. Okay? Do I know that? Well, I don't know. Okay? I mean, it does seem to me that you have very few samples. So the probability is, because I know that this is a low average, but if there are few samples, maybe it's not a real thing, right? If I had 10 people with this and 1 million people with that, it might not be so unusual for, even if they were equally good, for my small sample to happen to have gotten unlucky. Okay? But we're having discussions about this, and this is therefore good. Any questions about that? Anyways, we could have made this plot better. Does anybody see the plot well enough to want to see a way to make it better? By the way, if you're in TV land, these are on my webpage. So if you go back to where the lectures are, this is now online. So if you want to see it better, if it's too blurry on television. Do I have any questions about this one? Well, one thing I noticed is that the range they have is kind of weird. This, I guess, the lowest point on the plot is 0.3. So it looks like these versions are catastrophic relative to that. But these had a success rate of 0.3. This had a success rate of 0.6. This is higher, but it's not nearly as catastrophic as maybe suggested by this. Yes?
Kind of like
When the detection rate is low is good. Okay? So do we believe that these versions are better? Okay? That might be what the question is. You're telling me lower is better. Do we believe that these versions are better? That would seem like if you look at this, that's maybe the message of the plot. Do I believe it? Probably not, because the company felt a reason to come up with later versions, and the later version was more popular. So, but we're having interesting discussions about this. This plot is interesting because it's telling a story. Any questions about that? Okay, what about this plot? People like this plot. Okay? To me, this plot is informative if you want to know the right way to nail a canvas to a wall, right? Shows you the positions that you should put the nails. Okay? What is it trying to show? Okay? If I'm guessing, it's showing me something here. Firewall presumably was a yes or no thing. It was a Boolean thing. Did you have a variable firewall or not? And did you have detections? Either you had detections or you didn't have detections, right? This is showing two Boolean variables, right? And it's showing something. I guess we learned that for all four possibilities, there is at least one example of this. Okay? But this seems like a weird way to show a Boolean, okay, as sort of a point on an XY thing. And I don't know what I'm supposed to see in these dots. So this, I'm not impressed by this particular plot. Any questions about that? I think people agree, right? What about this plot? What is this plot showing me? It's showing me for 4 different versions of Windows. What was the ratio of detected to undetected? And what do we see here? Okay, does this tell a story? To me, when I look at it, what do I see? I think, well, it's pretty obvious that since they were giving us a data set, they were trying very, very hard to make it so for each operating system, half of the items were from 1, half the items were detected, and half the items were not detected. Something like these splits being so close to 0.5 couldn't have happened by chance, I don't think. Except something weird happened here. Why is it that Windows 16 was skewed? Does anyone remember anything about the Windows 2016? Were there a lot of points like that or very few? Was that a common version or a non-common version of the data set? Does anybody remember? Yeah? So there were very, very few of these things. Okay? So why was it skewed? Well, maybe if they had an odd, if it was that they only had 6 of them, 6 out of 10 would have been something like this. Okay? it seems that for some reason, presumably the reason this was so low was it was presumably infrequent, and they didn't bother to make it perfectly skewed. Okay, they didn't want to lose the data from one of from one of the few examples of this thing. Okay, but there's a story. I'm learning something from the data set from this. Any questions? Okay, I think that's a decent plot. What about this one? Okay, this one here is showing me is a gamer versus, this looks like the account of the number of people who either are gamers or not gamers. Right? Does everybody kind of get that? As far as I can tell, this is showing me two data points. How many people were not gamers? How many people were gamers? Is my interpretation of that data right? Is this a good plot or a bad plot? You don't like it. Why don't you like it? What? The Y I'm assuming is a count or a frequency. That's because I see that there's a large number there. That's why I kind of figure that out. Doesn't, well, it tells us that there's more non-gamers than there are gamers. But why did they connect these 2 points in a line? What does this tell me? It's like a prediction that there are this many people who are half gamers. Would that be the way to interpret what this graph means? That's what I think the graph shows, but of course that's a meaningless thing, right? So this idea of plotting the Boolean seems like a bad idea. What about this one? Okay, this one is showing me two things on the same plot. Again, detection percentage and number of users by the number of AV products. So what does this show me? This shows me that the number of machines with two products, the biggest fraction of machines seem to have one antivirus product. Some have two. There are relatively few that have three, and there's a long tail that have everything on the sun. Malware detected. Again, I think higher percentage. The higher percentage is bad, right? If you have your malware detected, that's bad. Is that right? Just to fill that 10's ears. Am I right about that? Okay. So what does this tell me? That for the guys that had a huge number of antiviruses, of which there were very, very few, this guy, it looked like every one of the people with 7 antivirus products, they were bad. Does that mean it's bad to have 7 antivirus products? My guess is the fact that it was a 100%, okay, over here, meant that they were one or two incredibly inept system. There was one incredibly inept system manager who just kept loading on more and more antiviruses while leaving his machine open in some other way. Okay, that's what it tells me. There's one clown. It's not. That's what this big graph jump means. Generally speaking, do I think that with 0? Actually, it looks like with 0 is weird. Does that mean that there was nobody that had 0 products in that test set? Did anybody have 0 products? So there are a few numbers. Now, none of the ones with 0 products weren't hacked. But it's clear that that's a small enough point that it doesn't mean very much. Generally speaking, what am I seeing? That as you add to a certain point, as you add more antivirus products, it probably slightly reduced the chances of being hacked. I think I believe that. But I have something to talk about when I see this graph. Any questions? Okay, here's another. What about this one? Do people like it or not? This is showing What's the number of malware detections as a function of range of country identifiers? Does everybody see that? It looks like it bucketed the number of the country identifiers. Is this a good plot or a bad plot? Okay. Anybody have a feeling? Bad plot on television. Why is this a bad plot?
So the countries actually don't mean, the country number doesn't mean just an integer. You cannot bucket two countries together unless they are semantically bucketed, that poor countries in one bucket, first world countries in another bucket. If
Does
you're not
everybody
doing,
see that this is equivalent to sorting the countries by alphabetical order and saying countries that's names begin with A are different than countries that names that begin with C? Does that make sense? China is a country that begins with C. Congo is a country that begins with C. Canada is a country that begins with C. What do these countries have in common? That their name begins with C. Okay? This thing bucketed them on the basis of country identifier when the country identifier presumably had it was just a descriptive variable like a name. Okay? So, does it have labels on it? That's good. Do we know anything bad about this? It looks like these countries had more malware detected in it. What does that learn? That we shouldn't name our country somewhere between starting with an S and then starting with a U. Okay? We're not really learning anything, even though this is a nice looking picture. Any questions about that? What about this one? This one does not do any bucketing by country. What do we think about this one about countries? Good plot, bad plot. Shows you for every country identifier what was the percentage of malware detected. People like it, people don't like it. What is it? Okay. See people moving your hand. What's your feeling? Any feelings here? Well, what is it supposed? Again, if we knew what the countries' names were and we could look something up, that might be interesting, right? What's the most important thing you see on this figure, though? When I look at this figure, what's the primary visual thing that we learn? What's the meaning of the shading? What we learn from this is countries with low numbers have lighter bars than countries with high numbers, right? That's what I'm seeing when I look at this plot, right? It's quite a striking result. But does everybody agree that that's a meaningless thing? Okay? This is an example of what we'll later talk about as chart junk. Okay? They have a fancy graphic power to make a rainbow shade. Okay? It's not clear this reveals anything at all. Like it's pretty clear that it reveals nothing. Any questions? Okay. Yeah, let me keep going through this a little bit. Okay, genuinely, this is one that was a bar chart. I don't know what genuinity is. I don't know if that's a misspelling or that was a real variable name. But it does show me that somehow there was a difference in infection rates between things that were unknown and things that weren't. That's kind of does stand out to me. Okay. What about this plot? This plot is showing me the build number. This is the detection rate by build number. Who likes this graph? Who doesn't like this graph? Okay. Who likes it? Who doesn't like it? Okay. Yeah. What does this show? Again, it would seem like it's plotting the build number. Okay. And it's connected. We can argue whether the build numbers themselves are interesting numbers. Okay, because I mean, there's a big gap here, And it's less clear that that's an important big gap here. But what was the thing gained by connecting the lines? What you're dominated by is not a sense of, is it getting better or worse? You've got this crazy line that's doing nothing, right? Why do we have something like this? Why did something like this come along? It said, you say same build number had different detection rates? No. I'm guessing that there was a frequent issuing of builds here, which very few people had. If one person had if only one person had that build number, the detection rate was either 0 or 1, right? My guess is this is showing me low frequency things and jumping around. Okay? So this I don't think is very, I don't think I figured that out, but frankly, I don't know what else I'm supposed to learn from the plot. Let's take a look at this one here. Okay? The one here is, what do you think about this one? It says gaming, not a gaming machine, gaming machine. Two pie charts. Is this a good plot or a bad plot? What do people think? Okay, who here thinks good? Who here thinks bad? Okay, I saw about 5 goods. I saw one twitch for no. What's my reaction? Ostensibly, it looks like a meaningful thing, except how many numbers are being represented in this graph? You're using a lot of ink for this thing. Many numbers are being represented? Okay, how many numbers are appearing on this plot? I hear 4. Is it 4? It's only 2. Notice that if you knew this number and this number, the other number is defined by it. This is using 2 circles to tell me 2 numbers. Okay? And what is the lesson? Do I think I'm learning something about is gaming machines good or bad? Well, frankly, they're so close to each other. I suspect that there's probably no difference if there's a gaming machine or a non-gaming machine. So I don't really get the story, but I also will say this is not a very, let's say, data-rich plot. Okay, it's about as unrich as you can make it. Any questions? Okay, so I can go through a bunch of these a couple of other ones. I think everybody sees what's wrong here. The data that they think is worth showing. Obviously, where I want to see data, I'm not seeing it, right? What is this black mass here? Can anybody guess what that black mass is below the plot? Labels. Okay. Was it helpful that they displayed all the labels for every point? Okay, obviously not. Okay. So, what is interesting here? What I hope I've convinced you of is that people in this class who are all smart people, none of you were dumb if you got into Stony Brook, okay? Possibly misguided, but not dumb, okay? What would be the, it's clear that doing visualization, sorry about this. Let me get this back. It should be clear that doing visualization is a harder thing to do than I think people think. And so what I'm going to want to talk about for the next class or two is to go through and start to think seriously about how visualization works. This is one of these things that it's important to develop some kind of an aesthetic to. Okay? Visualization is important because you can find, if you want to find mistakes in your processing, there's, if you run a machine learning model and it tells you got an F score of 0.71, that tells you absolutely nothing of whether you have a bug or not. On the other hand, if you take a look and draw the appropriate figure, you'll be able to see why you've got a problem, where the problems are. Okay? Looking to see if your data observes the distribution that you want. You'd like to look at data and observe patterns that tell you something about what's going on. You'd like to be able to, once you recognize a pattern, claim maybe that there is a story here that needs to be told. Okay? And like I say, many of you are going to build machine learning models, okay, often, okay, in the course of your career. If you try to train it on data that you haven't looked at, your data almost always has problems. And I guarantee you that you're not going to end up with as good a model as it would be if you understood what was going on. And visualization is usually the technique to help you understand it better. So again, as I showed you, and that I told you in class, a large fraction of the graphs that I see from students, and from in papers also, are often terrible, okay? Because you need to kind of think about what you want the graph story that you want the graph to tell, okay? You want to make sure that you're looking at enough of your data that you really get a sense of whether of what is there, okay? And you know, if you're looking at, let's say, a pre-processing, a cleaning thing, you want to look where there are violations of your assumptions, okay? Is there something weird that you did that you're going to regret? So the principle, one of the, you know, let's say, classic motivations for scientific visualization is an example that people call Ascombe's quartet. Who was Ascombe? He was the guy who made up this quartet of data sets. He came up with these 4 data sets. All 4 of these data sets have 11 points, I believe. They all have the same mean of the x's, the same mean of the y's. They have the same variance of the x's, the same variance of the y's. The correlation between x and y is the exact same in all these point sets. The question is, can you look at these and tell me, are these point sets doing the same thing or not? By every summary statistic, these point sets look like they should be the same, right? Can anybody look at these numbers and tell me anything about these point sets? What? The fourth one, the fourth one you're able to tell something about. Fourth one, you've noticed that X thing looks kind of funny, right? Okay, so that one looks kind of weird. I think you could tell from that one. Good eye. Anything else you can tell from any of these numbers? What their story is? I certainly can't. But if you draw graphs of these things, suddenly you will see that all 4 of these points even though they are the sets, even though they have the exact same summary statistics, tell completely different stories. What is the story of this plot? Story of this plot to me is you have a correlated data set with natural fluctuations, okay? Certain level of noise. What is the story of this data set? One outlier. You shoot this guy, and suddenly you got a perfect linear fit, right? What's the story of this guy? This is the one you were able to see. You've got one outlier, okay? But here the line is actually horizontal, okay? What was the story of this one? Okay? Story of this one is kind of like a quadratic fit. It's not a linear thing at all, right? Nothing wrong with that. But the lesson here should be clear. If you looking at the numbers or just looking at the summary statistics, doesn't really tell you what's going on. A well-designed visualization does tell you what's going on. So next class, which is not on Tuesday because we have fall break, we're going to start talking a little bit more about what the principles of building good visualizations are and bad visualizations, which I think is an incredibly useful skill in just about everything you do. Any questions? Okay, thanks for your attention. And I will see you guys not on Tuesday, but on Thursday, right? Okay, thank you.